Autophagy in the hypothalamus plays a remarkably influential role in how the brain regulates appetite, satiety, and overall energy balance. While autophagy is often discussed in the context of peripheral tissues like muscle or liver, it also operates actively within the central nervous system, particularly in hypothalamic neurons that monitor the body's nutritional status and direct behavioral and physiological responses. The hypothalamus integrates hormonal and nutrient signals such as leptin, insulin, ghrelin, and glucose, making it the command center for hunger and energy expenditure. Autophagy in this region ensures that neurons remain responsive to these signals, helping the brain accurately gauge when to eat, how much energy to store, and how much to burn. At the cellular level, hypothalamic autophagy supports neuronal health by clearing out damaged organelles and protein aggregates, preserving synaptic function and sensitivity to circulating metabolic hormones. When this process functions optimally, it fine-tunes the activity of appetite-regulating neurons, particularly two key populations: those that express AGRP, a GUD-related peptide, which stimulate hunger, and those that express POMC, pro-opiomelanocortin, which promotes satiety and energy expenditure. Research suggests that autophagy is essential for the proper signaling of these neurons. For example, under fasting conditions, autophagy in AGRP neurons increases to help mobilize lipid droplets and maintain neuronal firing, which contributes to the sensation of hunger and the drive to seek food. Conversely, after feeding, autophagy in POMC neurons helps process hormonal cues like insulin and leptin to suppress appetite and shift the body toward energy use and storage. When autophagy in the hypothalamus is disrupted, as seen in genetic models or during obesity, this finely tuned signaling balance breaks down. Leptin resistance develops, meaning that even when fat stores are high, the brain no longer registers the signal to stop eating. Likewise, insulin signaling becomes impaired, disrupting glucose sensing and promoting continued food intake even in the presence of excess energy. This creates a feedback loop in which defective autophagy contributes to appetite dysregulation, which in turn promotes further fat accumulation and hormonal imbalance. Over time, this cycle can rewire the brain's response to food, making it harder to resist cravings or regulate portion sizes, even when consciously trying to eat less. The implications are powerful. Impaired autophagy in the hypothalamus may be one of the hidden drivers of persistent hunger, overeating, and difficulty losing weight. But equally powerful is the fact that hypothalamic autophagy is responsive to lifestyle and metabolic conditions. Studies have shown that caloric restriction, intermittent fasting, and exercise can restore autophagic function in the hypothalamus and reverse some of the neuronal resistance to leptin and insulin. These changes not only help normalize appetite, but also improve the brain's ability to promote fat burning and energy balance. The result is a more intuitive alignment between food intake and energy needs, an effect that supports long-term weight control and metabolic health. Furthermore, some naturally occurring compounds such as resveratrol, curcumin, and spermidine have shown promise in boosting brain autophagy and supporting hypothalamic function. While much of this research is still in early stages, it suggests that dietary and supplemental strategies may one day be tailored to improve central nervous system autophagy, offering targeted tools for appetite control and obesity prevention. Supporting hypothalamic autophagy may also benefit mood, motivation, and cognitive flexibility, further reinforcing the link between metabolic and mental health. It's also important to remember that the brain's autophagic processes, like those in the rest of the body, depend on rhythm. Constant snacking, poor sleep, and chronic stress all interfere with the body's ability to activate autophagy in the brain. By allowing the brain regular periods of nutrient rest through structured meals, fasting windows, or overnight recovery, it becomes more likely to restore proper appetite signaling. The goal is not to suppress hunger entirely, but to reestablish a healthy cycle where hunger arises when needed and naturally subsides after eating. Altogether, autophagy in the hypothalamus represents a compelling mechanism by which the brain exerts control over food intake and energy regulation. It bridges the cellular world with behavior and physiology, showing that internal repair processes can shape not just metabolic outcomes, but also how we experience hunger, fullness, and motivation to eat. By supporting this system, we enhance the brain's ability to maintain balance, a critical step toward long-term, sustainable weight regulation and overall well-being.